Greetings, your majesties of the East and good gentles all. My name is Rosina von Schaffhausen, and this video is in support of my entry to the Crown's ANS Championship in AS 55. In this video, I will explain the modern pattern analysis technique that I used on a German 16th century brocaded tablet weaving pattern book. This is a math-based technique, but don't worry, I learned the math that this is based on in high school, and it is now in the 8th grade Common Core standards. It requires no algebra and barely any numbers. All you really need are 4 basic geometry terms. The technique that I'm going to explain is a part of symmetry analysis. Symmetry analysis is when we look at a piece of art to see what types of geometric symmetry it has. Symmetry is when we can pick up a piece of art and flip it over, turn it around, or move it in some direction, and when we put it back down, it looks the same as when we started. The first type of symmetry you will need to know to apply the technique I used is whether a piece of art has translation symmetry. A design has translation symmetry when you can shift the design in some distance and some direction, and when you're done, the design still looks the same. The type of patterns I analyzed all have repeating patterns in one direction, so they all have translation symmetry. Only one direction means a design is one-dimensional, so the analysis I am conducting is one-dimensional symmetry analysis. It is possible to have repeating patterns in more than one direction, like in fabric or wallpaper, which are two-dimensional, or even with three-dimensional objects. Also, you can have symmetry where you move the piece, it changes color, like with heraldic counterchanging. These are all types of patterns that you can analyze with symmetry analysis. See my symmetry analysis topic references in my paper for more information if you want to know more. But for this project, I am analyzing brocaded tablet weaving patterns, so they are one-dimensional patterns. If you want to know if you can use a one-dimensional symmetry analysis on a piece of art, check if it has translation symmetry in one direction only, but not counting moving the opposite direction. The second type of symmetry I use is mirror or reflection symmetry. This means you can flip the design over and it looks the same. You can also think of a design with reflection symmetry as having two halves, where each half is a reflection of the other. Notice that there's a line in the design where the mirror goes, or a line that you flip the design over. In a one-dimensional repeating pattern, there are only two possible directions that line can go. It can go parallel to the direction of translation. This is called horizontal reflection. Or it can go perpendicular or at right angles to the direction of the translation. This is called vertical reflection. One-dimensional repeating patterns can also have reflections in both these directions at the same time. Notice that a one-dimensional pattern can repeat in any direction, but you can turn any design so it repeats horizontally. Also, you can assume the design is infinite, even if it ends in the piece of art. We generally ignore slight inconsistencies in the pattern that we can tell are not intentional. Or if there's a curve in the design, from wrapping the design around a piece of pottery or around this rowel spear. Few artists can perfectly recreate the design in each repeat, and in period examples, some of a design may have worn away over time, so we ignore these when looking for symmetry. However, you should be careful of tiny details in the work that are intentional, as they could affect the symmetry. For example, at first glance, you might think that this pattern has mirror symmetry, but the over and under detail in the vine work means that the two sides of this motif are not perfect copies of each other. If you have a hard time visualizing whether a piece of art has a particular symmetry, and you don't have physical access to the art so you can pick it up and move it around or hold a mirror up to it, you can use a computer to do the moving for you. Take a photo or screenshot of the design, paste it twice into a Word document or an art processing program, and use the imaging tools to flip, turn, and move one copy of the image while keeping one copy the same, and compare. The third type of symmetry that one-dimensional repeating patterns can have is rotational symmetry. This means you can turn the design around a point for less than a full turn, and the design will still look the same. The point is the center of the rotation, and the smallest angle you can turn, and it looks the same, is the angle of the rotation. You may have noticed from the examples shown that there are many different angles that could be the angle of rotation of a design. However, with one-dimensional designs, the only possible angle of rotation they can have for rotation symmetry is a 180-degree angle, often called a half turn. So we don't have to worry about the angle of rotation in this analysis and only have to look for half-turn symmetry. Notice that, like with reflection symmetry, you can have a half turn and other symmetries too. The last type of symmetry that a one-dimensional repeating pattern can have is glide reflection symmetry. This symmetry is a combination of a translation and a reflection, but looks differently than just a translation or just a reflection. The translation part of a glide reflection has to go in the same direction as a translation of the whole pattern. So in one-dimensional patterns, it will go horizontally. And the line of reflection part of the glide reflection is also horizontal. The pattern made by a line of footprints in the sand has glide reflection symmetry. Just like with other symmetries, a design can have glide reflection symmetry and other symmetries too. In addition, if a one-dimensional design has horizontal reflection symmetry, as in these two designs, it also has glide reflection symmetry automatically. Now that we have all the types of symmetry a one-dimensional repeating design can have, we can combine them together. The International Union of Crystallography, or IUC, has symbols for all the possible combinations of symmetries that a one-dimensional repeating pattern can have. This is called the IUC notation. There are other types of notation used for these patterns, but I chose to use IUC notation for this project. This notation consists of 4 symbols, where the first one is a letter P. This indicates that the pattern is a one-dimensional pattern. The second symbol is the letter M, if there is a vertical reflection symmetry in the pattern, and a number 1 if there is not a vertical reflection symmetry in the pattern. The third symbol is a letter M if there is a horizontal reflection in the pattern, a letter A if there is a glide reflection but not a horizontal reflection in the pattern, and 1 if there is neither a horizontal nor a glide reflection in the pattern. You can think of the letter A as standing for alternating, as glide reflection designs look like they are alternating on either side of the center line. The last symbol is a 2 if there is half-turn symmetry, and a 1 if there is no rotation symmetry at all. So if you've done the math, you'll notice that there are 12 possible combinations of symbols in IUC notation. However, sometimes when you combine 2 symmetries, you automatically get another one. For example, combining a horizontal reflection and a vertical reflection is the same as a half turn. So it turns out that there are only 7 possible combinations of symmetries that a one-dimensional repeating pattern can have. The simplest design in the 7 possible symmetry groups, the design can have just the translation that makes it a one-dimensional repeating pattern and no other symmetries. This is group P111. The design can have a vertical reflection, but no other symmetries other than the translation, and that's group PM11. There can be a group with only a glide reflection and no other of the special symmetries, or P1A1. You might have a horizontal reflection, which means you get a glide reflection automatically, but no other symmetries in addition, or P1M1. You can also have just the half turn, and not any of the other special symmetries, or P112. And then you can have a more complicated combination with a vertical reflection, a half turn, and a glide reflection, but no horizontal reflection, and that's group PMA2. And lastly, you might have all the possible symmetries: the vertical reflection, horizontal reflection, glide reflection, and half turn, and that's group PMM2. If you see a design and want to tell which of the 7 possible combinations of symmetries it has, you can first check for each individual symmetry, and then use the information about the IUC notation to determine which group your design is in. Or you can follow a flowchart. There are a number of flowcharts available on the internet and in the sources in my paper. Now that you've seen the math background behind my research project, you can take a look at the summary of my research analysis of a 16th century German brocaded tablet weaving pattern book, or you can read my research paper to see a fully detailed analysis of the patterns in the pattern book. I also used the symmetry analysis to reconstruct a pattern that is unfinished in the period manuscript.